Hey guys, my name is Suyog Mapara. I'm a software engineer at Meta. I have spent most of my career working on a domain of large-scale systems, and last four of those were at Meta. Today, me and my colleague Ali are going to tell you about a system called Zelos which we have developed. Zelos stands for Zookeeper on Delos, and it is intended to replace a decade-old Zookeeper usage at Meta. So let's start with a quick recap of what Zookeeper is. As you may already know, Zookeeper is an Apache open source project. It started its life in 2008 in Yahoo. Back then, Yahoo engineers realized that distributed application of all kinds needs two things in common. They need some place to durably store their metadata, and they also need some means for coordinating execution between the two application servers. Since nothing was available to them that they could have used off the shelf, they ended up building custom one-off solutions which made their applications brittle. Yahoo engineers realized that this is an opportunity to build a centralized solution to solve this problem, and thus the Zookeeper was born. As you can imagine, this problem is not actually specific to Yahoo. And so when Zookeeper was made open source, the rest of the industry started adopting it, and Meta was no exception. Zookeeper was introduced to Meta in 2010, back when it was still called Facebook, if you remember, and initial use case for Zookeeper was the configuration management. Since then, Zookeeper has exploded in popularity in Meta, and today it is used by over 100 teams. This includes critical infrastructure services like container orchestration, service discovery, configuration management, and package distribution. As you can see, Zookeeper has truly become the bedrock of infrastructure at Meta. As you know, with great power comes the great scaling challenge. And indeed, Zookeeper was stretched to its absolute limits to accommodate the needs of our customers. Over the years, it became harder and harder for us to keep scaling Zookeeper vertically without changing the API, as we were hitting hard walls on multiple dimensions. To overcome these limits, we were exploring ideas along two directions. First direction was try to extend Zookeeper API with primitives that can be implemented efficiently on a server side. We were looking into some projects like server-side semaphores in this area. The other direction was, of course, try to scale Zookeeper horizontally by building some kind of a native sharding support. We were also looking into this direction with some ideas such as ensemble split. These projects actually saw some successes, but we were not able to get as much out of these projects as we had hoped. The reason for that, as it turns out, is that Zookeeper API is significantly intertwined with its underlying consensus protocol, which makes changing one without changing the other difficult. And since we were not able to keep up with the increasing usage, our customer ended up building custom one-off solutions on top of Zookeeper. And we actually found ourselves in exactly the same situation as Yahoo engineers were a decade earlier. This made us very clear to us that a new system is needed to replace Zookeeper at Meta. With this understanding and learnings, we went to drawing board and started thinking about how we want this new system to look like. It would come as a no surprise to you that we wanted this new system to have a layered design so that every aspect of it can be replaced at runtime. Secondly, given how widespread the Zookeeper usage is at Meta, it also meant the new system need to provide an API and semantics identical to Zookeeper, at least initially, so that there is no work required from our customers while migrating to this new system. In a longer term, we would then leverage flexibility in our design to significantly outscale Zookeeper. Next, Ali is going to tell you about how we went about designing this new system around these two design principles.
Thanks, Yo. My name is Ali, and I'm a software engineering manager at Meta. I have been at Meta for close to 8 years and have worked on several projects. A common theme across all of them has been building core infrastructure for Meta services and products. So let's get into how we approach the first design principle of layer architecture and reusable components. We had a few colleagues at Meta working on a project called Delos. This project was started by Mahesh in 2017 with the intent of making it easy to build storage API offerings. Delos itself is not a storage service, it is a platform, and it has been presented in many forums previously, like SOSP, OSDI, and even Mahesh gave a previous system at scale talk. It also won the Best Paper award for its concept of virtual log in the OSDI forum. So let's actually see what Delos provides us out of the box. At the bottom of the stack is the virtual shared log. It is this abstraction that cleanly separates the API from the complexities of distributed consensus protocols. As an example, the first time we built Zelos, we actually built it on a log that was built on top of Zookeeper. It was easy to build. We were able to validate the correctness of the Zelos APIs and move fast. As soon as we had a log that did not have any other external dependencies, we call this log the native log. We were able to quickly switch out the Zookeeper log and use the native log without any massive migrations or an open heart surgery into the code base. The replicated state can take a form of a key value store to a relational database. It can also take the state of a Zookeeper API. Now, for any replicated state, we need a storage layer. Zookeeper itself had an in-memory store, which was really hard to change to something, say, like RocksDB. Delos provides a clean abstraction of a storage engine, making it easier to store the underlying storage layer. So, for example, in production, we use RocksDB as a storage layer, but in unit tests, we use an in-memory setup because it's easy to initialize and set up. Now, engine stack is where we actually get the customizability from. This is similar to layers in a network protocol. Each layer adds an additional functionality. For example, at the beginning, when we wanted to check the consistency of data across all our ensemble members, we built an offline consistency checker that was pretty clunky and error prone. When the time came to build an online consistency checker that ran a running checksum on the log and data, we built it as an engine. Now, don't get me wrong, it was not easy to build this engine, but the rollout was really simple. We just had to add another layer in the stack of engines, flip a flag, and roll it out. So far, we have discussed what Delos provides us out of the box, but this was not enough to build the Zookeeper API. So before I hand it off to Suyog to talk in a bit more detail about what went in bridging this gap, let me give you a quick primer of the Zookeeper API itself. Zookeeper provides a CRUD API that allows users to store data in a hierarchical representation. It is analogous to a file system where you have directories and files underneath, but only in this case the directories can actually store data. In Zookeeper, you can also be notified about changes to the data tree. So for example, if client 1 creates a node and client 2 and client 3 are interested in this node, they can set a watch on the existence of this node. So as soon as client 1 creates this node, client 2 and client 3 will be notified. Zookeeper is built around this concept of sessions. Now, sessions can be used as a lease. Users can create ephemeral data on a session, and the underlying session keeps updating this lease by session timeout. If the client itself disconnects for more than session timeout, all its ephemeral data will be disconnected. So in this example, there are 3 clients and all of them create an ephemeral node when they connect to Zookeeper. They also have a watch on each other's ephemeral node to figure out who is alive and who's dead. So as soon as client 1 disconnects, after session timeout, all its ephemeral data will be deleted, and client 2 and client 3 will be notified that client 1 is no more alive. This and the concept of watches can be used to build very powerful coordination primitives like distributed locks, semaphores, and even failure detectors. So operations on a single session are executed in order. This means that if a client sends requests A and B, Zookeeper will execute request A before executing request B. This ordering only applies on a session. It does not apply across sessions. So having said all of this, I'll hand it again back to Sio, who will deep dive into what went into bridging this gap between Zookeeper needs and what actually Delos provides.
Thanks, Ali. So now that you understand Zookeeper API, let's deep dive into Zelos architecture. If we were to implement a standard consistency model, like say sequential consistency, on top of Delos, it would have been actually straightforward. All we have to do is, for every write request, append an entry to Delos' shared log. Delos would then replicate this entry and give an upcall to every replica, and then replica can apply that change locally. Here, local view is a component that takes an operation on a high level API, which is file system like API for Zelos if you remember, and converts it into one or more operations on a low level API of a local storage, which is typically a key value store like API. So this is a workflow for a write. For a read request, it's actually simpler. Every replica can independently execute read against its local state as long as it's sufficiently advanced. And that's it. Unfortunately, though, as Ali told, Zelos session add an additional layer of complexity. We are required to execute two operations in session in exactly the same order that they were issued. So if we have two writes, then they can actually be reordered before they are appended to Delos' shared log. This is because Delos has no notion of sessions. So it treats those writes as concurrent and it can freely reorder them. To bridge this gap, we added our first engine layer called session ordering engine. It plays the same role in our stack as TCP plays in a networking stack. So essentially, it gives an illusion of an infallible order stream on top of Delos. Internally, it actually maintains a queue of requests that are not acknowledged, and it resends those requests if they are dropped or reordered by Delos. And on the receiving side, it ensures that those requests are delivered in exactly the order they were sent. Next, we also need to ensure that we don't execute any reads until all the writes in the session are applied locally. So we need some place to hold those reads until they are ready to be dispatched. This is done by a component called request processor. Think of it as a scheduler for Zelos. All requests are registered with the request processor and it ensures that they are only dispatched according to session order. Together, these two components implement an ordering aspect of session that Ali told about. Now let's see how leasing aspect of session is implemented. If you recall, client is periodically sending heartbeats to keep its session alive. On a server side, we have a component called local session manager, which is running on every replica and it receives those heartbeats. Its job is to track all the clients that are connected locally via their sessions and expires any sessions for which the client fails to heartbeat within a pre-configured session timeout. Now, as you know, client can be connected to multiple replicas throughout the lifetime of a session. So it is entirely possible for two local session managers running on two replicas to disagree on whether session is alive. To address this, we added our second engine layer called Global Session Manager. Its job is to aggregate the decisions made by individual local session managers, reconcile any differences, and come up with a globally consistent view of what and which sessions are alive at any given point in time. It of course uses Zelos' shared log to drive this consensus. Think of it as a distributed leasing layer for Zelos. And since, as you can see, it is implemented as an engine layer, its implementation is actually not specific to Zelos. This means that it can be used by any Delos-based application that needs a notion of a distributed lease. Together, local and global session manager implement leasing aspect of sessions. Finally, we have a watch manager running on every replica, which tracks all the watches installed by the clients which are connected locally. It is also tracking all the changes that are applied locally and then it triggers any watches for which the corresponding paths are updated. Together, these six components implement complete Zookeeper API on top of Delos. And we were able to get to this state from initial design to first cluster running in production in mere 8 months. Of course, this is not the end of story. Replacing a battle tested system like Zookeeper is never going to be this easy. We needed to match it on every single dimension, and getting feature parity was just the beginning. It truly has been a long journey since that point. For example, when we compared performance of Zookeeper versus Zelos, while Zelos was able to store significantly more data, in fact, an order of magnitude more data than Zookeeper, its performance of read and write throughput was inferior to Zookeeper. This probably would come as a no surprise to you, since you're comparing a system that stores its data in memory versus a system that uses database. The database means that we have a 10x more data that we can store, but it also means our reads and writes are slightly slower than Zookeeper. Now, remember that we wanted Zelos to be a drop-in replacement for Zookeeper, and so we need to address this gap. Addressing a gap in write throughput was relatively easy. For that, we added our final engine layer called batching engine. As its name suggests, it batches the requests on their way to Delos. This helps amortize the cost of replication as well as database application. And it also helps reduce scheduling interrupts we do to request processor while processing a write request. On the other hand, improving Zelos's read throughput required us to get creative in our scheduling algorithm that we use in request processor. So now, session ordering requires request processor to execute either one write or multiple reads at any given point in time. Since our reads and writes are coming from database, they are slower than Zookeeper, which made our critical path longer. But we also had our own advantage over Zookeeper that Delos provides. Delos has a notion of a cheap logical snapshot. So it means that we don't have to actually execute entire read in the critical path. Instead, we can actually do minimum possible work and then rest of the read can execute out of order. And then finally, we need to make sure that the responses are reordered back in the session order before they are given to the client so that they're not aware of this reordering that happened. This work greatly helped improve read performance of Zelos. And with projects like these, we were ultimately able to meet or exceed Zookeeper's performance on all dimensions while keeping all of our existing advantages. Next, we turn our attention to understanding our dependencies. Since Zookeeper was running at the bottom of Metastack, its dependencies are extremely well understood. And we are constantly testing how Zookeeper reacts when those dependencies fail. In early days of Zelos, we didn't have similar testing. And so once, there was a misconfiguration of a dependency which led to a huge production outage. Since, of course, as you would expect, we have significantly invested in the dependency testing for Zelos since those days under an initiative called resiliency parity. This topic is actually covered in depth in an earlier talk that Chris and Jai give, so please check it out if you're interested. And finally, with feature performance and resiliency parity, we are ready to take critical production workloads away from Zookeeper, and Ali is going to tell us how we did that.
Thanks, Suyog. So as Suyog explained to you, that we went from design to the first production use case in mere 8 months. Now, for the first production use case, we actually worked with a customer and built a very specific migration plan for them. Now, with more than 100 teams using Zookeeper, it would be very difficult to have a specific migration plan for each one of them. So we had to build something generic. Now, building something generic was challenging because Zookeeper and Zelos underneath are two completely different services with different consensus protocols underneath. Also, the Zookeeper API is fairly large and very nuanced, making it even more challenging. And the third challenging bit was that we didn't want our customers to do any work and we did not want them to have any downtime during this migration. So, let me tell you how we went about this challenge. So during the migration, we wanted to give an illusion to clients that they are actually experiencing a leader election on Zookeeper. When a leader election happens on Zookeeper, the clients actually disconnect from Zookeeper. And once they reconnect, they are able to go about their business as if nothing happened. This is more important for sessions that have ephemeral data and is important that they connect before session timeout. Now, this time when they reconnect, they'll actually connect to a Zelos ensemble. So the clients would have atomically switched databases within seconds without even them noticing. Let's zoom in how we did this. So since Zookeeper and Zelos talk different protocols, we had to build another client called the Migration ZK client, which actually wraps the Zookeeper client and the Zelos client. Now when this client starts up, it actually connects to the Zookeeper ensemble. We also set up a Zelos ensemble, but we set this up in observer mode. By that I mean that it does not take writes and is actually listening to transactions happening on Zookeeper through the ZAP protocol. We also define a notion called the barrier node, which is actually a special node in the Zookeeper data tree. Now, as soon as this node is created, The Zelos ensemble will learn about it through the transactions. And as soon as it learns about it, it reconfigures itself into a quorum, at this point it is able to take writes. Now the migration ZK client also attaches a watch to the existence of this node. So as soon as it is notified about this watch, it'll disconnect the Zookeeper client, tear it down, reinitialize create the Zelos client, and it'll connect to Zelos. And by this simple mechanism of using the Zookeeper consensus protocol, we were able to actually swap the databases without even the client knowing. So we were able to use this mechanism and migrate 50% of our workloads. And this includes some of the critical workloads like Twine, Log Device, and many other customers. So looking forward, our primary goal is to completely deprecate Zookeeper from our fleet. Now, as we went about the migration, we learned a bit about how our customers use Zookeeper. And we realized that not a lot of them require the strong ordering guarantees provided by Zookeeper. We actually want to use the composability provided by Delos to relax some of this. As Suyog had mentioned in the talk, that the monolith design of Zookeeper made it really hard to innovate on it and scale it. As Facebook infrastructure grew, so did the demands of our customers on Zookeeper. And one single ensemble was not enough for their use case. So they had to build custom sharding solutions on their own, which really took a really long time. We want to take advantage of Delos's layer architecture and build some of these building blocks in the platform itself so that all the apps built on top of platform can reap the benefits. This work is really challenging and is in early stages, but we are stoked about this direction as it will help alleviate a lot of problems that our customers face today. Thank you for listening to our journey and hope you enjoyed the talk.